All right, good afternoon, everyone. So just to kind of recap what we talked about last time, we are now looking at this classification problem. We started by looking at the binary classification problem where essentially your targets are categorical but just one of two classes. And so we said that we're going to focus on this linear classification scheme where you can think of it as a two-stage process. The first stage uses a linear model to, this variable z, we call it a score. It's like an intermediate quantity. You can see it's just a linear function of the weights and the bias, also a linear function of your features. Once you get that score is a real number, then you threshold it to turn it into a binary outcome, which you report as your predicted label. And so we spent a lot of time focusing on how we get these parameters B and W, how we design them. But we also, so as part of that, the most popular way to do that is to come up with a probabilistic model that relates the true labels to the true scores Z. And that model, the most popular version of that model looks like this, which is this sigmoidal function. And just we said that this idea of a probabilistic model is not really new for us because we can also interpret all the least squares that we were doing as using a different probabilistic model where the targets were Z, which is exactly the same sort of Z here, plus additive white Gaussian noise. And when you go through all the maximum likelihood derivations, you come up with least squares as the solution to that problem. So all we're doing here is we're saying for this case where we have one of two binary labels, we saw earlier that if we use least squares, there's issues with imbalanced data sets. So rather than doing that, we're going to think of a different probabilistic model, and that's what we were kind of focusing on last time. It's one based on sigma. Sigmoid, sorry. And then we went through maximum likelihood, and we did a derivation that said, okay, if we're given a bunch of labels yi, feature vectors xi, how do we maximize this likelihood, which is the probability of all the training labels given all the training features and our parameters. We went through a derivation which hopefully as we do more of these becomes more and more familiar to you. But our derivation essentially, as always, what we start with is we start with these probability of these vectors, yi, and then we use independence to break them into a product of probabilities of the scalar labels, yi. And then we also know that with maximum likelihood, rather than maximizing the likelihood, we can also minimize the negative log likelihood. It's typically what we do. So when we apply the negative log, we get the negative, and then this product turns into a sum of the logs of these guys. And then we kind of came to this slightly tricky spot because here we're dealing with a PMF, and we didn't really state the model in terms of a PMF. We stated it in terms of the probability of the event that y equals 1, given the other stuff, and the probability of event y equals -1. So we had to use this little trick. I think of it as like a switching variable. You can also think of it as one-hot coding. But the trick was how do we write like these things in terms of those expressions? So the trick was we insert these variables here that the first one turns on when y equals 1 and otherwise set goes to 0, takes this out. And the other one, this one turns on when y equals -1 and otherwise goes to 0 when y equals 1. So that allows us to bridge between this PMF model and these models. And finally, we got this longer expression. After that, it was just straightforward algebra to go through this stuff with the logs and so on. And eventually, we got this expression for the negative log likelihood. So that is how we're going to train our models. So this is kind of to summarize. if you're given a bunch of training data, X and Y, XIs, YIs, this is the optimization problem that we have to solve to compute the parameters B and W. And it's not something we can write down like a least squares thing on paper. It's something we have to do with an optimization algorithm, and we'll study this a lot more intensely in the next unit. But for now, it's enough to know that it can be done with straightforward algorithms, and sklearn implements them, and so we can use them in our lab. And then there's a slightly different version of this. If the labels are 0, 1, then this term here changes to yi. And this is known as the binary cross-entropy loss most commonly. And there was a question from a student just now who said, well, I've seen this binary cross-entropy loss talked about in deep neural networks, and is there a connection? Actually, so that's used, and also the sigmoid is used in neural networks, and is there a connection to this stuff? And the answer is definitely yes. The connection is that in a classification deep network, the last layer is just linear classification. So all the stuff we're doing now will be exactly just the last layer of a deep network when we get to that. So you then train those networks most commonly using exactly this loss that we derived, and you can implement that with the sigmoid function we talked about. So these are all building blocks for where we're leading up to. And let's see, so the last things we talked about were that in practice you tend to add some regularization, either L2 or L1. If you don't, and if your training data is linearly separable, you can get into a problem where the optimization algorithm will just keep making the weights bigger and bigger and bigger the more iterations you let it run. But if you add this regularization here, that will keep things finite. And you can also do feature selection when you add the L1. You can figure out which subset of features is most important to predicting that classification, that label. And then there's, to implement this in scikit-learn, it's very similar to how we implemented the linear models. You just use logistic regression instead of the previous one that we were using, and you can set a few parameters. We'll talk more about some of those parameters today. And otherwise, you do your log reg.fit and then .predict, and you can measure accuracy. So that's just kind of a review of what we talked about last time. So this time, we're going to repeat a lot of these things again, but for the case where we have 2 or more classes. So, specializing on the case where we have strictly more than 2 classes. When we have 2 classes, we can do things like we did before. When we have more than 2 classes, we need to do things a little bit differently. So again, just to kind of start from the beginning, what we're saying is, let's say you're given training data, X, Y pairs. X is a vector, but now the Ys that you get are, they represent different categories. So this is categorical target data. And so we don't want to think of them as, even though they may be specified to you as integers from 1 through k, you don't want to think of them as like class 1 is less than class 2, which is less than class 3, and so on. They're really like cats, dogs, cows. It's like different stuff, categories. And so our objective is to predict the category of the label, the categorical label from the features. So here's just one illustration on the right that you can see where we're plotting. So this is the case you have 2 features, d equals 2, but you have 10 possible different categories, and they're plotted with different markers. So these are the training examples, like one category is here, another category is here, another category is here, and so on. And so we would like to build a classifier that you could think of it as carving up this space into different regions, where whenever the test sample falls in, let's say, this region, then that classifier will report that it thinks it's of the class of the red star class. And here you can see for this particular classifier, we have some very nonlinear boundaries. So that would not be a linear classifier. As we'll see, this would be some sort of nonlinear classifier. but it just kind of shows you the general notion of these decision regions, which we talked about previously for the binary case, but here you can have many different decision regions, like in this case where we have capital K equals 10. So that's our objective, is to design a classifier that takes in the feature vector x, makes a prediction y hat on the true label y, and we hope that our prediction is correct with high probability. Okay, so I just want to make, just quickly again, emphasize the difference between regression and classification here is that in classification problems, we have categorical targets, while regression problems have ordinal targets. So it's not about the target being discrete or not. You could have a regression problem with a discrete target. So for example, if you wanted to predict, let's say, on Amazon, there's star ratings 1, 2, 3, 4, 5 stars, and you want to predict the star rating for a new product. You want to think about that as a regression problem, not a classification problem, because 1 star is definitely less than 2 stars, definitely less than 3. Those stars are ordered. That's an ordinal variable. It happens to be discrete, but that's not really that important. If I predicted, 4.7 stars, even though that's not an integer, you can understand what that means, what 4.7 means. But if you have categories, if you have 5 different categories, it doesn't really make sense to predict something that's in between your categories. That thing doesn't exist. So again, if the target is discrete but ordinal, you're probably dealing with a regression problem, not a classification problem, and then you want to use the right tools for that problem. So in the next homework assignment, for the homework assignment for this unit, I'll give you some kind of challenging applications to think about, where you'll have to say, is this regression or classification? And sometimes it's a little tricky, and sometimes there's actually different ways to think about the problem. But this is sort of the main rule, is think about whether the target is categorical or not. Think about how you'd approach the problem. All right, any questions about the big picture classification with multiple classes? Yes?
Can you give an example of the target is discrete but not? This is like probably a regression problem. Is there can you give an example of where it's discrete, ordinal, but it's not a regression problem?
Let's see, discrete and ordinal, but it's not a regression problem. Okay, I'll come up with one. Let's say I show you a picture of an animal, and I want to know how many. I want to know how many legs are on that animal. And so when I show you a picture of something, maybe one of the legs is hidden behind it, right? So it's like it's a cat. It's a cat, but you can only see 1 or 2 legs. So if you want to predict how many legs are on there, you don't really want to count legs. You don't want to say 1 leg is less than 2 is less than. It's kind of like, I got to figure out what kind of an animal this is. Once I know that, then I know how many legs are on it, right? So that's a little bit tricky, a little bit convoluted. So that's where this kind of, even though number of legs is, it's either 1, 2, 3. How many animals naturally have 3 legs? Right? It just, so in some cases the problems are kind of tricky, and you got to think through a little bit, how would I actually do this? But for most problems, they're simpler, and it kind of boils down to this notion. Okay, sure. Yeah. If you think through about how you would have to approach that particular problem, I show you an image. I want to know how many legs are on this creature. Number of legs in that sense is really a property. It's kind of like, it's like a category. There's 4-legged creatures and maybe 6-legged insects and 8-legged spiders, right? It's kind of an attribute of what's really a category. So it's a little bit convoluted, but there are some kind of tricky questions like that on the homework, just to try to make you think, how would I approach this? How would I approach this with machine learning? And sometimes there's like multiple good approaches. You could, in some cases, approach something as a regression problem, or you could approach it as a classification problem. You might get like okay results in both cases. But in other cases, it's more clear cut, you know. And if you just want to predict like number of stars for a movie rating or something like that, it's like, okay, it's discrete, but it's definitely ordered. There's no question about that. Okay, all right, yeah.
So for this two features in k equals 10, is the two features mean that there's like two different weights on our x values in our equation?
Yeah, so so the x, those are our features. To say that there's two of them means that that's a two-dimensional vector. So, you know, if you want to plot it, there's like two scalar values. And then y is a scalar value, but it takes one of k possibilities. So there's k different kinds of markers here. But the number of features, which we usually use d for, that's just the dimensionality of x, or like the number of different things we're using for prediction. Okay. Right. Okay, so multi-class classification is a lot trickier than binary classification, and there's a lot of different ways to do it, but the main approaches that people use can be kind of split into two groups. Usually, let me just preface it by saying, if you can re-express this multi-class problem as maybe a set of binary problems, and we have these great binary methods, that gives us a nice way to approach it. And so a lot of methods are constructed that way. It's really kind of like putting together binary classification methods to make a multi-class classification method. So that's what we're talking about right now. And there's basically two different traditional ways you can put together binary classifiers to make a multi-class classifier. The first one has two names. Sometimes it's called one versus rest, sometimes it's called one versus all. But this is the idea. So for each class k is indexing through our different classes. So like here, we have blue, red, and green. So I will start with blue, and I will think of, I'll kind of formulate a classification problem, which is blue or not blue. So this would be a linear classifier that would be, you know, pretty good classifier for blue versus not blue, right? So that would be one classifier. Then I do this for red. I do red versus not red. That's this one. And then I do green versus not green. I do this one. So for each of these classifiers, you would get some sort of score z of k, right? So let's say like there's a new test sample that happens to be over here. So for blue, you could see it's on this side of the line. That means I think about it as more as a not blue, but maybe it's close to the line, so I'm not really that confident whether it's blue or not blue. On the other hand, if I think about a point over here for my green classifier, that's going to give me a score which is pretty far on the green side of that line. So I'm pretty confident that that is green. And then meanwhile for red, I'm pretty confident that that is not red. So those are the outcomes that I get for those three individual classifiers. So one approach is I could just say, let's look at those three different scores. And whichever score is largest, that's the one with the highest confidence. Let's choose that one. So, so in this case, you know, maybe, let's see. So another thing to remember is that the way that the score z works is that when you're on this side of the blue line, that would be positive, and then this side would be negative, because this is like not blue. So that's, you know, as we go out further here, that's like more and more negative. So when I'm looking at this idea of finding the highest, most confident z, for the green one, it would be positive and large. This point for the blue one would be negative and small, and this point for the red one would be, you know, negative and large in magnitude. But among those three, green would win, right? Because it's actually the only positive one. So that's sort of the idea behind one versus rest, is you formulate these individual classifiers like you're either in K or not in K, and then you compute scores for all of them, and then you look, whoever has the highest score, that's who you award the classification to. Is that idea making sense? So if you do that here, it would actually result in these boundaries because, yeah, I mean, if you think through it, that approach would result in these boundaries. So this is, I would say, the most common approach to building a multi-class classifier with a set of binary classifiers. And this is what we're going to focus on. Yes.
If any points are in the middle, they wouldn't be in any class.
So, okay, let's think about the middle. So let's say I'm here. So that would be, my blue score would be small and negative, but it's something, right? My red score would be even more negative, and my green would be even more negative, so I would choose the blue, right? And so here, this is the point where I'm equidistant from all three boundaries, right? And that's why all the lines meet there.
Also with the other boundary, right? Between green and blue and...
Exactly. Yeah. So this point is like equidistant to those three boundaries. Okay. So is that making sense then, that method? Okay. So another method is 1 versus 1. And so what you do now is you look at every class pair. So for example, I first look at blue versus red. I forget about green entirely. And I build a blue-red classifier, which might look like this. And then I do blue-green. Maybe I build a classifier like this. And then in this case, the only other pair that we haven't considered is red-green. So those would be the classifiers I would make. In general, when we have more classes, there's going to be more pairs than there are classes, right? If I have if I have 4 or more classes, you would actually have more pairs to evaluate than you would in this case. However, one advantage is the number of data samples in any one of these problems is less. These guys have less data samples than these. So there's sort of, computationally, even though you have more of these scores to compute, there's less samples to process per score. So there's sort of a trade-off there. But in any case, now you compute like these confidences for pairs. Of course, you want to always leave out, you would never do like blue versus blue. So you have pairs Z sub KL where K is different than L. And then to navigate between all those, what you do is if you want to do blue, you would basically sum up for all the scores. So let's say, okay, so like if we're focusing on a particular K, we sum up all the scores L not equal to K, and we get this sum score that is now dependent on K, and we maximize that over K. So that's sort of how we're going to merge all these paired scores to finally get the estimate of K. So just 2 different approaches. The second one is a little bit less common than the first, but it is used. Actually, when we study support vector machines in Unit 7, the scikit-learn's implementation is actually based on this. So that's how it's done there. But anyway, we're going to focus for now on this approach for the rest of this unit as a way of building multi-class classifiers.
Is there any reason why it's more common, or like is the other one perform slower or better?
That's a good question. So one thing about this method is that the data sets are smaller. So if you have a method whose complexity grows very quickly with the data set size, like an SVM grows quadratically, you want to keep that as small as possible. So I think that's why it's used there. But otherwise, this is simpler. So and maybe it's more efficient when it grows linearly. So yeah, I'm not sure, but I think maybe just the simplicity and everything lets us focus on this. Okay, so all right, so let's go in a little bit more depth here. If we're talking about, again, linear classification and logistic regression, we can put these ideas together. So we want to train multiple binary linear classifiers with 1 versus rest. So, there's basically 2 steps here. the first step, as usual, is to compute scores. Second step is to quantize those scores. So in the binary case, there's only one score we computed before we quantize it. Now, we're actually going to compute a different score, zk, for each of our capital K classes. So just the idea that I described over here. So we have multiple scores. And then, as I discussed, we just find the index of the biggest score, and that is what we report as our guess. So, so that's sort of the main idea, and we somehow want to use logistic regression to do the fitting. So here, there's going to be two different options, sort of a simpler option and a more complicated option that works a bit better, but it's more complicated and computationally as well as intellectually. So the simple method goes like this. Just train K separate binary logistic regression models. Okay, so coming back to this picture, for example, if I'm doing blue versus not blue, if I'm training this with a logistic regression, I know exactly how to do that. I would take this as one class of training data. I would group all these guys into another class of training data, and then I would basically compute this model based on those. Then, next I would do my red model with logistic regression, and that as my training data, and so on. So that's very straightforward, but maybe we could do better, because somehow we're fitting each of these classifiers on its own without thinking about the other classifiers. So maybe there's a way of jointly designing all three classifiers that would work better than this individual approach. So that is the second option here. It's called multinomial logistic regression, the title of the slide. And so what we do is we're going to use a slightly more complicated probabilistic model. It's very similar in spirit. It's kind of like if you extended that sigmoid to multiple dimensions. So this is what you do. So the new model says the probability that the true label is in class K, given the score vector z, because now we have a bunch of these scores, takes this form. So the numerator is very similar to what we had before. The denominator is just summing all the different e to the power z's for all the different scores. And basically the reason, you can kind of say that the reason why we need this denominator is that when you sum this over the different possibilities k, it must sum to 1, because those are the, there's capital K different possibilities, and so when you sum across all the possibilities, the total probability must be 1. So that's essentially what this is doing for us. And so it's, the important part is really the denominator. You're taking these scores and you're exponentiating them, and then you're normalizing to get a valid PMF. Okay, this is called the softmax. It's sort of like the extension of the sigmoid to something a little more complicated. The name softmax comes because when one of the zk's is much bigger than the other zk's, then when you look at the different values output by this over the different k's, you'll find that one of them is approximately equal to 1, and all the others are approximately equal to 0. So it's kind of like a one-hot encoding. It gives you something like a one-hot encoding when one of your scores is much greater than the other scores. So anyway, that's kind of the main idea now. Is this is a new probabilistic model. And so because it's a new model, when we do maximum likelihood, we have to modify our derivation a little bit to handle this new model. It's not so different, but maybe we can go through it now and just see what the differences are. Okay, so again, one difference compared to the binary case. Now we're essentially going to use one-hot label coding, where you could say that we are designing, capital K different classifiers, right? So each one of these has an intercept B and a weight vector W. So here's all my different b's. I'll put them together in a vector b. Here's all my different w vectors. I'll put them together in a matrix w, just as columns. And so what we'd like to do is we'd like to maximize over the parameters b and w the probability of my training labels given my training features and the parameters. And we know that's maximum likelihood. We also know we can equivalently minimize the negative log of that likelihood, or with the independence assumption, that gives us a negative, and then the sum, and then the log of the individual training samples yi, given all the features and everything else. So the main thing we need to do now is these yi's here, these guys are integers. These are members of the set 1 through k. Right? So what we're going to do, I guess I wrote it over here already. Okay. We're going to translate that representation into binary vectors using one-hot coding. So we studied this previously with features, now we're doing it with targets. So we're going to call this boldface vector, boldface yi. Okay, again, the I means it's for the ith training sample. This guy is an integer, but this guy is a one-hot vector. So, and in particular, it's all zeros, except there's a 1, and the location of the 1 is determined by the value here. So let's say if this value was 3, that would mean that the 1 is in the third position in the one-hot encoding. Mathematically, you could say yik, which is the kth entry of this, is 1 when this yi is k or is 0 otherwise. Okay. Is the one-hot encoding making sense? Okay, so that is what's going to allow us to do this kind of bridging between this PMF expressed in these integer yi's and the derivation for which we actually need to use these probability of these events. Like what's the probability of the yi training label equaling k? So because for this, we have this expression from the previous page. But we don't have a good expression for this. So similar to what we did when we did the binary case, we're using these switching variables. And these switching variables are exactly the elements of our one-hot encoding. So the key point is that only one of them is non-zero, and it takes on the value 1. So we can actually replace this thing, negative log of this PMF, with a sum over these switching variables of this log of this event. So the way that works is if you, let's say that yi takes on the value 3. So what's going to happen is all these guys will be 0 except the third position. And when that guy comes alive, that is going to have yi equals 3 here. So that is how we can transition from these scalar values, this PMF, to these values here. It's exactly like the switching variables we used last time, except there we only had 2 of them. Now we have k of them. Is this sort of making sense? Okay. And now that we have that done, that's the hard part. Then everything else is simple because we have this expression on the previous page. It was just this. So we just need to take the log of that. And we have log of the numerator minus log of the denominator. Log of the numerator is just zik. And then minus log of the denominator. We can't really simplify it much. So this is what we have. And there's one final simplification we can do. So, okay, we're going to take this one term, move it over here, and then let's look at the remaining term, which is this times this. So the first thing you note is that the sum depends on k, little k, but there is no little k in this quantity, so you can actually pull that in front of the sum. And then all you're left with is the sum of these indicator variables, these one-hot variables. So for every training sample I, when you sum over this vector, it always equals 1. There's always a single 1. It's in some position, but when you sum it, you get a 1. So essentially, that sum over yi turns into a 1. You don't have to write it down. And then you just have this guy alone. Okay, so that's how we finally get this expression here. And that is the guy that we plug into this sum over our training samples. And so finally, this, bringing in the sum of the training samples, this is the optimization problem that we need to solve to do this MLR, multinomial linear regression. It has a similar flavor to the binary case, but it's definitely differs in the details. This is known as the cross-entropy loss commonly. And similar to in the binary case, in practice, we add like an L2 regularization or an L1 regularization to prevent the parameters from going to infinity if things are not, when things are linearly separable. Or in general, maybe we have correlation in our features, in which case this could help, or maybe we want to do feature selection, in which case that could help. So finally, we have to tune alpha. As always, we do that with cross-validation. But this is really all that we can do for simplifying the expression. We can't really simplify it further. We just need to basically attack this with some sort of algorithm. But it turns out that this is, again, a convex optimization problem, so there's no problem. You can build algorithms to do this in many different ways. So we'll come back to this again in Unit 6, but for now, it's enough to know that this problem is solvable, and we can do it in sklearn.
Is regular cross-entropy the same thing as categorical cross-entropy? Or is categorical like a different equation?
I guess I'm not sure what you mean by categorical cross-entropy.
Like TensorFlow, you got a binary or you got categoricals.
Uh,
Sparse categorical. I didn't know.
Probably it's probably this. Yeah, probably this. Okay. Okay, so let's talk a little bit about the implementation now. So again, in scikit-learn, we have this logistic regression object. It handles both the binary and the multi-class cases. So the parameter that controls that, which is one of the more important parameters, is actually this. So remember how when you have multi-class data, it's two different ways to train it. You can either train it using these, you can train it using these separate binary logistic models, or you can train everything jointly, all the weights and biases jointly using this MLR. So that is controlled by this. So if you put in OVR, that is the simple case where for each K, it separately trains a one versus rest binary classifier using binary logistic regression. But if you want to use this more fancy stuff that we just derived, then for this OVR, you need to put in multinomial. And then it does the true multinomial logistic regression. What you find is that usually it works a little bit better, but it takes longer to run because it's computationally it's more challenging. Another important parameter here is you can see the penalty. You can choose L2 or you can choose L1. By default, it's L2. And depending on, so there's also another thing called the solver. So this tells you which algorithm you're going to use to solve this optimization problem here. And it turns out that some of the algorithms can handle L1 and some of them can't. So sometimes if you put in L1 here and then you try to use, I think liblinear, I don't think you can do L1. You'll get this error like that solver doesn't work, so you have to choose a different solver. There's about, I don't know, maybe 5 or 6 different solvers. They all have different speeds. Some of them are better with big data sets, some of them are better with small data sets, et cetera, et cetera. In theory, they should all give you the same answer if you run it long enough. But these are algorithms that you run for a finite number of iterations, and also if the algorithm thinks that it has, solved the problem because some tolerance is small enough, it will stop early. So you have some control over that. You have control over how many iterations it uses and when it stops early. And so the different algorithms will respond differently to those numbers. So finally, when you choose different algorithms, you might get slightly different values when you're done because they stopped at different points. But if you ran them for, for a long time, they should all give you the same result in the end because they're all trying to solve the same problem. Those are the most important things. And finally, so this is also important. C is going to be 1 over alpha. So that's the inverse regularization strength. So here you can see how it's set by default to a large number, 100,000. That's basically like setting alpha to a very small number. So it doesn't bias your weights too much. Okay, so that's how we would implement stuff in scikit-learn, and you'll get a chance to play with some of these things in your lab as well as in your final project. All right. So, yes, any questions about anything? Yep.
How is this different than deep learning? Is this deep learning just have all the transformations report and this doesn't?
Yeah, we'll of course study deep learning later, but basically like deep learning, it has a lot of, you do a lot of transformations where you try to get the features to work better with linear classification. You try to make them closer to linearly separable so that this stuff works really well.
And this is just the last layer?
This is just essentially the last layer, yeah. All right, any other questions? Okay. All right, so measuring performance in classification is a bit more interesting than in regression. Let's just start with the simple case of binary classification. Even there, it's kind of interesting. So when you think about what can happen in binary classification, there's basically 4 possibilities when you think about the true label and the estimated label. So if the true label is 1 and you get it, you correctly predict it, we'll call that a true positive. But if it's 1 and you guess wrong, you can call that a false negative because you're saying no, it's not on, but you're wrong, it's false. Over here you have if it's truly off and you think it's on, that's a false positive, and then true negative, not making an error. So there's really 4 different outcomes, and there's 2 types of error, right? False positive, false negative. Sometimes people call them false alarm or missed detection. So in some applications, there's really not a lot of difference. You care about them equally, like maybe in digital communications when you're transmitting bits that are 0 or 1, like if you got it wrong, 0 to 1 or 1 to 0, it's kind of all the same. But in other applications, there's a huge difference between those 2 different errors. So let's talk about one like cancer diagnosis. So let's say that you do not have cancer. So that would be true label is 0. But you go and you get tested and somehow your test comes back positive. Okay, so that would be a false positive. So I would say that that's not really that serious of a situation because what would happen is, yeah, you'd be worried, but then you'd get more tests done and you would find out that actually you're healthy and there's no problem. But if we consider the other situation, false negative, that's where you have cancer, you take a test that comes back negative, you think everything's fine, and so you don't worry about it, but meanwhile the cancer grows, and by the time you test again, it may be too late. You might die. So here you can see there's a huge difference between false positives and false negatives, and so when designing a classifier, you actually might want to take that into account when optimizing your classifier and make sure that the false negatives happen much less frequently than the false positives, because that's it's a much more serious error to cause. So so that's why when we talk about binary classification and you measure the performance, it's not just as simple as saying what is the accuracy. So the accuracy is one way to do it. And let's talk about some of the most common metrics. So accuracy is just the probability that y hat, your guess, equals the true y. And if you want to think about it in terms of numbers, like let's imagine that these are just integer numbers you did like 100 different experiments, and so you have 4 different numbers which will all add up to 100. So if you want to, from your experiment, estimate the accuracy, you'd essentially be counting the total number of errors you made, the total number of correct tests you made over the total number of tests you made, all 4 of them, right? So that is, like I said, that's one way. The interpretation there is how often is your test correct? But as I just described, for cancer diagnosis or some other applications, it's not about accuracy. You actually care to measure false positives and false negatives differently. So one example that's very common in the literature is called precision. This is the probability that you guessed that the truth is positive given that your test is positive. So one way to think about that in terms of the table is when you say given that y hat equals 1, it's like you're restricting yourself to this column. And then you're asking, in that column, what is the fraction of y equals 1 versus the alternative? So you get this. So that's precision, or in terms of the cancer, like given a positive test, how often is the patient actually cancerous? Another way to look at it is recall, where you're flipping the conditioning. Now it's the probability y hat is 1 given y equals 1. So given that the patient has cancer, y equals 1, how often is it detected? And here we can think about it, this conditioning y equals 1 is sort of like saying focus on this row of the table and then look for the fraction of this over the total. So that's where we get this. And sometimes you care about both of those, but maybe in a slightly different way, than accuracy, because accuracy, so I guess what's sort of interesting about this is the true negatives never actually make their way into either of these metrics. So even if you want to, let's say, average these, the average you would come up with is going to be a little different than accuracy because true negatives is definitely a part of that metric. But anyway, the typical way that you average these two is through the F1 score, and that is where you do the averaging in the inverse domain. In other words, you use the harmonic mean. So what you do is you invert the precision, invert the recall, look at their average, and then invert that. So that is also a pretty common metric that is going to give you some combination of precision and recall, but it's going to be different than accuracy. Okay, so these are probably the most common ones in machine learning. Now, if you go to the medical literature, they use sensitivity and specificity. Turns out sensitivity is exactly the same as recall, but specificity is a little different. So specificity is what's the probability that y hat equals 0 given that y equals 0. So here, sensitivity is like given a sick patient, how often does the test agree? Or given a healthy patient, how often does the test agree with the truth? Okay, so these are all different ways to measure accuracy of classification. And so which one you use will depend on your application. Okay, any questions on any of these? Okay, so here's an example of how you can compute some of these things in sklearn. Not surprisingly, it's very easy. So what we're going to do is we're going to do this with tenfold cross-validation. So we're going to make our k-fold object like we've done before. Here's the number of folds is 10. We're setting shuffling to true. And sometimes in the demos, I set the random state to a fixed value so that every time you run the demo, it's the same. Otherwise, every time you run the demo, it's different. And then if I run the demo, then it doesn't agree with all the lecture notes where I copied and pasted. So I just fix the state. But it's not necessarily something you want to do in practice. Because if you fix the state in practice and you keep optimizing and optimizing your code, what you're really doing is just optimizing the code for this particular state, which is maybe not what you want to do. You're going to overfit to that state. Okay, so this is how we can do the cross-validation. It's very simple in that we can just use one command to do it called cross-validate. We're going to give that command this logistic regression object that we already set it up. We're going to give it our full data. It's going to split it into test and training folds. We're going to tell it how to do that by giving it this k-fold object. And then we're going to ask it to compute a number of different scores. And the scores are given in this vector here: precision, recall, F1, and accuracy. And then it's going to return everything in this data structure, and we can extract the different scores. It's going to give us test and training, precision, recall, accuracy, F1, so we can extract what we want. And then each of these will be a vector of scores over the different folds. And so we need to take the mean to get like the mean precision. And we can also compute the standard errors by computing the standard deviation and then dividing by the square root of the number of folds. So we can compute the mean quantities as well as standard errors. And then here we can print them out. And you can see for this cancer data set, we got pretty good numbers, like mid-90s for all metrics. And then the standard errors are roughly around 1%. So it tells you that we can have some confidence in these values. Okay, so that's how we can do things in scikit-learn. Any questions about this? Okay. All right, so there's another kind of freedom we have that we haven't really talked about yet, which is how we do our quantization or our thresholding. So remember that when we do our linear classifier, we have two steps. The first step computes a score, and then based on our, let's say our model for, this is our logistic model, we can convert that score, which is a real number, into a probability, something between 0 and 1, which we can think of as a confidence. And we can either threshold this, let's say I just want to get a y hat that's either a 1 or a 0. I just want a binary answer at the end of the day. I could threshold z at some value, or equivalently, I could threshold my confidence at some value. And until now, we focused on thresholding z at 0, which is equivalent to thresholding the probability at 0.5, right? That's what we kind of said to do until now. And that is certainly an option. It's the most common option. And it turns out that if you do that, so that's setting this threshold on the probability at 0.5, that is the optimal thing to do when you want to minimize the error rate. That maximizes your accuracy. But as we said, there's applications where you actually care more about precision than recall or vice versa. And so you might not want to minimize the error rate or maximize accuracy. You might want to do something else. And one thing you can do is you can choose a different threshold, a threshold that is not 0.5, something between 0 and 1. And it turns out that when you do that, you can actually trade off between your precision and your recall score. So here is the threshold t. As you move it from 0 to 1, your precision increases and your recall gets worse. So if you care more about precision than recall, you probably want to have your threshold somewhere over here where your precision is doing better than your recall. Because if you're saying precision is more important to me, then you want to weight it more by choosing a threshold somewhere over here. Similarly, you could also think about trading sensitivity for specificity. And so here we have specificity going up with the threshold and sensitivity going down. So you have different options just with how you threshold your score to get a different hard classification at the end. Any questions on this idea? Okay. So, and there's another option we have too, which is to think about, so instead of looking at, let's say, precision, recall, sensitivity, specificity, we could think about the false positive rate and the true positive rate. This is a little bit more common in electrical engineering and radar and stuff. They talk about basically false alarms and probability of detection. That's essentially what these are. And so you can plot these two on one graph. So here we're plotting So as the threshold, this is the threshold t. If you start out with a high threshold, you'll be somewhere over here. As you change the threshold, you get different combinations of these two guys here. So this is actually the curve here of them versus threshold. But like, at a particular threshold like 0.4, I'm going to get some combination here and there. And if I plot those two things on a curve, it ends up somewhere over here. So this is just another way to visualize things. This is called the receiver operating characteristic. And this shows you, as you change the threshold, exactly how you can trade off between, in this case, the true positive rate and the false positive rate. So the best place to be is in this upper left corner, ideal. So this is where your true positive rate is 1, like, you're always, whenever the sample is 1, you are guessing y hat equals 1. And in that corner, your false positive rate is 0. So whenever it's truly 0, you're never guessing y hat is 1. So that would be the best place to be, is that upper left-hand corner. So you can see that, like, it's not exactly clear, like, is this point here closer to the corner, or this point here closer to the corner? It's like there's some sort of trade-off. As you get near that corner, these are all good values. In practice, you might say, look, I really need that my false positive rate is at least false positive rate is never more than 0.1. So you might say, okay, that I need to be on the left side of this, so I'm going to choose this. That might be your design constraint. It really depends on the application, but and maybe for a different application, you're content with a false positive rate of 0.2. So that will all affect the threshold you choose. So someone might say, well, I want to design my system, but I don't know exactly which threshold I'm going to choose at the end of the day. I want sort of a system that works well for many different thresholds. So one way you can do that is you can optimize the area under the curve. So if you think that is basically the area under the curve is this whole area here. In the ideal case, this blue line would be going, this blue line would be going all the way up here, and your area under the curve would be 1. That's the ideal case. You can never get more than that. In practice, this curve is like this, and when you integrate it, it's a number less than 1. But if you just say, I'm going to design so that I'm maximizing the area under the curve, it gives you a threshold independent way of doing your optimization that is, it's more general than, let's say, maximizing accuracy, because that's like a very particular thing. Here you're sort of saying, there's all these different trade-offs that I can make, and I want sort of a design that works well over a range of trade-offs. So this is a pretty popular approach, is to maximize area under the curve. And this is also something that you can compute with sklearn with this ROC curve and ROC AUC score. And so, for example, for this experiment, breast cancer demo, we're getting 99.6, 0.996, which is pretty good. I'd say very good. So, but you can see that if we had even a better design, maybe it would be up there and we could do even better. Okay. So these are just the different kinds of ways that people design these binary systems. And let me just very quickly say that when you move to multi-class classification, you get way more possibilities of what can happen, right? You have like k-square different possibilities. So people don't so much focus on like precision and recall and all that stuff as much. You can kind of think about this table as a whole, call it a contingency table or a confusion matrix. And it basically tells you, like, if the true label is 1, how are your errors spread out? Or if the true label was 2, how are your errors spread out? You can sometimes see, like, maybe there's one of these that has a huge error rate, and then maybe that you could then try to figure out what's going on with that particular case. Is there a way of improving my system so that so that it works better for that particular case. But so one important thing is when you look at these kind of tables, you often want to normalize the rows of this matrix so that they sum to 1. And if you do that, then the table becomes very interpretable. You can look at the normalized table, and the k-th entry is just the probability that y hat is L given y equals k. And also, the diagonal terms show you the probability of correctly choosing k given that the truth is k after you normalize it. Okay. And finally, if you want to know, okay, well, like what is the average probability, not, for a given class, you just average those diagonal terms, but you have to weight those averages by how often the true label is in that state. So, if one of these guys is much more common, then you really, if you care about average accuracy, you want to make sure that its error rate is low, because that will count more when you do this overall average. The very last thing I want to say is that sometimes data sets have imbalanced labels, meaning when you look at the distribution of your training samples, and maybe even your test samples, you might find that certain cases show up much more common than others. So if I have a total of k classes, you might find that certain possibilities happen much less frequently than 1 over k. And this can be a serious issue. So let me just give you an example. Let's say that you're detecting COVID in a patient, and the population you're testing, only about 1% of the people are sick. And so you say, okay, why don't I just design a test that always says that the patient is healthy, because then I'd be correct 99% of the time. It sounds pretty good, right? But it's a trivial test. It always reads positive. So that's another case where looking at average accuracy in these cases is sometimes very misleading. You really care about maybe what's happening with the rare classes, the classes that don't show up. And so if you train your model for something like average accuracy and you have these imbalanced labels, it will just learn to do what's good for the majority class, and it might come up with a totally trivial design. So there's different ways to deal with this. One way is to use a different metric in your training. Another pretty simple way is just to resample your data. So you look at all the training samples from the minority class and you just copy them. Copy and paste them until there's as many of them as there are the majority classes. You just equalize your data set size with copying, and then you run it for maximum accuracy. You run your model. You can sometimes change the classifier to work differently. There's various approaches you can use. I just put a few links here, different articles about this. And this could be super important in your own applications if you work with imbalanced data, because if you don't handle this correctly, you can get completely meaningless results. So that's the last thing to say for today. Apologies, I went a bit longer than I should have. And that's the end of this unit. So what we're going to do, we're going to basically switch. Let's see. So today is Wednesday, right? So we're going to focus on doing some review in preparation. We have a midterm Friday in a week. So we're going to do a bit of review. I'm going to go through all the stuff until now, spend a whole day on that. And then we're going to eventually move on to Unit 6 on optimization. And then, next Friday will be your exam. You won't have any homework due next week, or any quiz or any lab, so you can spend the entire week reviewing. And then we'll get back. You'll be assigned homework for this. Will be due the week after your midterm, and quiz and lab again. So we'll take a break from all that. All right, see you guys next time.